All right, hello, all of my thermodynamicists in training. So I promised you a video or screencast about our discussion on ideal solubility, and mostly just looking at the resulting plots. So we had the cooling crystallization curve, and then we also had a plot for water and ethanol where we were looking at freezing point depression. Okay, so I promised you a video to help you prepare for the exam and to help you study. So here it is. Okay, and so, right, we're mostly just going to look at the pictures and read through them. Okay, but what I have open is our Chapter 11 notes that are posted. And so when I talk about ideal solubility, the idea was I have a crystalline solid in equilibrium with a saturated solution. Okay, and so the general picture when we talk about solubility is I have a mixture containing two components, say water and acetaminophen, right, Tylenol. Okay, we know acetaminophen is a solid at room temperature. It's going to have a pure component melting point greater than that of water. So when we talk about crystallization, we're talking about acetaminophen, the component with the higher pure component melting point that's going to precipitate out a solution. Okay, and so at coexistence, at saturation, what we have in coexistence with each other is crystalline acetaminophen in equilibrium with a saturated solution, right? And by saturated solution, you can imagine, the experiment, say from general chemistry, trying to find, say, solubility of salt, in which you add salt a little by a little, right? Maybe you have a little, stirring bar in there until finally, salt begins to precipitate out a solution, right? As soon as precipitate begins to form, right, we know that our solution is saturated. Okay. And so the first assumption we made, right, so here's my isofugacity expression. Fugacity of my liquid is equal to the fugacity of the solid. First assumption was, right, in the spirit of Chapter 11, where we're talking about ideal solutions, is that my liquid phase is ideal. Okay. And, part of the goal of this is, this ideal solution approximation is a major approximation. It isn't necessarily always all that good, but the resulting models will allow us to capture the basic underlying physics of the process, which is great for us in terms of learning about all these things. Okay, so we're going to assume solution phase is ideal. Our other assumption is that with respect to the solid, we're going to assume that we have pure acetaminophen, so pure crystalline component 1 in coexistence with that saturated solution. Right, so we're assuming that our solid is pure of our component with the highest pure component melting point. And so this assumption of a pure solid is in general very good. Okay, so what's nice about expanding our fugacities like this is now we have an equation which is explicit in X, so we can directly solve for X, where X is the mole fraction in solution at saturation, right? How much of component 1 can I dissolve in my solvent? Okay, and so then I have a ratio of fugacities, fugacity of pure solid relative to pure liquid at the same temperatures and pressures. Okay, so that instantly makes me think of differences in molar Gibbs free energies, right, at the same temperature and pressure. All right, and so we went through the exercise then, where we could relate that to the enthalpy or change in Gibbs free energy upon melting or fusion. And if we assume that the enthalpy of fusion is constant and equal to its value at its pure component melting point, we get this final expression for the mole fraction solubility. Okay, so again, the approximation that the enthalpy of fusion is constant and equal to its value at its pure component melting point is an approximation. But it'll allow us to get to a model, this equation, that'll help us, that will capture the important physics of the problem. Okay, and so the last thing I'll note before we look at the picture, all right, where we're trying to go with that is this term on the right hand side, which is just in terms, it's just dependent on pure component properties, right? We want to get this in terms of terms we can actually physically measure to be able to compute my mole fraction solubility. Okay, and so the one thing I'll note in terms of what makes calculating this so challenging is, if component 1, my solute, is acetaminophen, right? Acetaminophen has a melting point, much greater than room temperature. Okay, and so this corresponds to the fugacity of, pure solid acetaminophen in equilibrium with pure liquid acetaminophen. So if I'm at, say, 1 bar, but I'm below that pure component melting point, right, this liquid phase corresponds to, hypothetical subcooled liquid state, right? It's not something, I can readily obtain in a laboratory, right, which is what makes, calculating this part so challenging. Okay. But anyways, right, we have this final expression, and so what this tells us is that if I know the enthalpy of fusion or melting of a pure solid, right, at its melting point, and that pure component melting point, I can use that to estimate the mole fraction solubility in solution. Okay, and we said, what's nice about these models is even, with these approximations, if they're not super accurate quantitatively, they do capture the correct physics, right? And so if I look at this expression, we can begin to ask questions, right? So as temperature increases, does x1 increase or decrease? Right? So as temperature increases, can I dissolve more or less of my solid in solution? Okay. Well, I know that my pure component melting point is going to be greater than T, right? I'm assuming I have, say, a solid at my temperature of interest. So as T increases, this ratio is going to become smaller. So this becomes 1 minus a smaller number. Okay. So then overall, since enthalpy of fusion and T1M are going to be constant and positive, that would mean that my right-hand side is going to increase. So that means then x1 is going to increase, right? And remember, this is an exponential relationship. So as temperature increases, solubility is going to increase. Okay, cool. As enthalpy of fusion or T1M increases, and so what this is getting at is when I think about dissolving a solid in solution, you can kind of picture it as a two-step process. Where in one, I'm going to take my solid and I'm going to melt it. I'm going to melt it to form liquid component 1. Then once I have liquid component 1, I'm going to mix that with pure solvent to form my final mixture. And in fact, you could derive the same equilibrium expression in that way. And so if I think about that first step, then the first step is taking component 1 and melting it. All right. And so if I think about solubility is melting and then mixing, right? And it should make sense. If I'm going to dissolve a crystalline solid, in that crystalline solid, I have a nicely ordered substance in which my pure component 1 or my component 1 molecules are interacting with each other. So in order to dissolve it, I need to separate those component 1 molecules and solvate them in my solvent. All right, so I need to break those pure component 1 intermolecular interactions. So my enthalpy of melting or enthalpy of fusion of pure component 1, right, should be a measure of, the energy of separating those interactions. And so if I think about, a couple of different solids, right, the solid, with the higher pure component melting point and higher enthalpy of fusion, is essentially harder to melt, right? It has stronger intermolecular interactions, which cause it to melt at a higher temperature and with a higher enthalpy of fusion. And so if I look at this equation, right, as my enthalpy of fusion or enthalpy of melting increases, what happens? So as delta H1M increases, hold on. So as delta H1 and or T1 increases, it becomes harder to melt, and X1 decreases. So this one I'm gonna have to work through, right? So 1 minus T1M over T. So when I look at this term, what's important is T1M is going to be greater than T. So when I look at this term, then this is 1 minus this number is going to be greater than 1. Why? Because the pure component melting point of component 1 is going to be greater than T. Otherwise, it would be a liquid at room temperature, right? So this T1M has to be greater than T. So 1 minus this, right? This term in parentheses is going to be negative. So as delta H1M increases, the right-hand side is going to become more negative. So if the right-hand side becomes more negative, that means that log x1 is going to decrease. Now as T1M increases, if I look at, say, this term, again, this term in parentheses is going to be negative. So this term here, right, is becoming larger, so this term is becoming more negative. And even if I were to distribute this, 1 over T1M through, all right, I'd get the same thing, because I'd have a 1 over T1M here minus 1 over T, right? And it'd be the same thing in that, as 1 over T1M increases, this term became smaller and smaller, All right, that would be constant. So this whole term is becoming right-hand side is becoming more negative. So as T1M increases, solubility decreases, enthalpy fusion increases, solubility decreases, it becomes harder to melt. Okay, and so then there's a couple of MATLAB scripts I provided. Okay, and so the first one is just label water acetaminophen. So looking at the solubility of acetaminophen in water. Okay, so acetaminophen is going to be solid at room temperature. And so I have its enthalpy of fusion or enthalpy of melting. So 27,700 joules per mole, so 27.7 kilojoules per mole. It has a melting point temperature of 443.15 Kelvin. Right, so it melts at a temperature much greater than 298.15, right, than room temperature. I've got my molar gas constant, just creating a vector of x1 values, right, and we're going to plot out a cooling crystallization curve, and then I'm going to solve for my saturation temperature. Okay. All right, so I'm just going to run this. Okay, so just water acetaminophen. We get this curve, and we're going to talk about this. Okay, so this is equilibrium curve for acetaminophen water. Okay, and so typically we'd call this a cooling crystallization curve. And so the general idea is when we worked up our ideal solubility expressions, we made this assumption that the solid in equilibrium with the saturated solution is going to be pure, component 1. All right, and so that's one of the reasons that makes crystallization such an attractive process is you can get pure product. All right, that's pretty awesome. So we also looked at and we said that as temperature increases, solubility increases. So we also expect that as temperature decreases, the solubility decreases. So if I have acetaminophen in water, and so say it's at saturation, okay, I can control the temperature, and by controlling the temperature, I can control the solubility, and hence control my ability to collect acetaminophen in my system. Okay, and so solubility decreases with decreasing temperature. So this is sometimes called a cooling crystallization curve, where the idea is if I take my system at saturation and decrease the temperature, I can get component 1 to precipitate out, right, which I can collect my desired product. Okay. The other kind of technique for crystallizing components out of solutions, anti-solvent crystallization, but that will involve non-ideal solutions, and is actually similar to entrainer selection, right? And it's going to be on this discussion. Okay. But all right, so how I can interpret this is I have plotted temperature in degrees C versus mole fraction in solution, all right, x1. Okay, so x1 being acetaminophen, my component, which is solid at 298.15 K. All right, so how we can interpret this is this line is my saturation curve. Okay, so if I have a mixture that's equimolar acetaminophen and water, but I'm at a temperature above that of my curve. Right? So say I'm at a temperature of 150 degrees C. So if I'm above my saturation curve, I would have a liquid phase. Right? So I have a liquid phase with acetaminophen and water. Right? It's not at saturation. Right? It's acetaminophen is completely dissolved in water. Okay. So say I'm at 150 degrees up here, equimolar mixture of acetaminophen and water. Okay. Then what happens is if I begin to decrease the temperature of my system, okay, once I hit my saturation curve, acetaminophen is going to begin to precipitate out of solution. Okay. If I continue to quench it down to say 50 degrees, right? If I quench that system down to 50 degrees C, what happens is acetaminophen is precipitating out of solution, and a new equilibrium state is going to form in which I have a liquid, saturated liquid at 50 degrees C, so it's going to have a mole fraction of acetaminophen of about 0.1 mole fracs in equilibrium with pure solid acetaminophen, right? And that's how cooling crystallization works, right? So, maybe I have some initial solution that is 0.9 mole fractions of acetaminophen, right? So, way up here at 200 degrees C, that would be a single liquid phase. So if I were to quench that temperature down to 50 degrees C, all right, so as soon as I get past saturation, acetaminophen begins to precipitate out of solution, all right, and as it precipitates, all right, as I quench that down right, a new equilibrium state's going to reestablish where I have, this saturated liquid in equilibrium with pure solid acetaminophen. So as I decrease the temperature, acetaminophen precipitates out of solution, and my liquid phase composition is just moving along this curve. All right, and so if I required, if you wanted to calculate actually how much solid you were collecting, you would just do a simple flash drum problem, where the solid that I'm collecting out the bottom is pure acetaminophen, and so the equations are actually rather simple to work with. Okay, but that's the general idea of cooling crystallization. Okay, it can be expensive because if I want to get essentially all of my acetaminophen out of solution, right, this would suggest quenching it down to essentially 0 degrees C. Right? Okay, cool. Right, so that's the idea of cooling crystallization. All right, and this would be a cooling crystallization curve. Okay, remember in this approximate model, we're assuming our solution is ideal, so we're not accounting for the interactions of acetaminophen and water, which would alter our cooling crystallization curve slightly. But this captures the basic physics. Oh, the one other thing I'll point out is when the limit of x1 is 1, right, that gives me my pure component melting point. Okay, cool. All right, so that's my cooling crystallization curve and how we read it. Okay. The other scenario we looked at, which is essentially just taking this equation and flipping it on its head. Right, so in the winter we add salt. We put salt on the roads. Right, the general idea being is when we add salt to water, we decrease its melting point. Right, and so talk about freezing point depression. We essentially just took this equation and we resolved for T. Right, and so even if you think back to this phase diagram, right, the idea is okay. Say we know, well, we would need to flip it, but pure acetaminophen melts at this temperature, right? As I add water to solution, right, the melting point essentially decreases, right? It moves. Okay. Well, hold on. I'm talking in reverse. Okay. Let me take it back. Let's go look at our water acetaminophen or water ethanol case. But you do see in this case that as I add so my issue is I need to think about this in reverse, right? Where I'm trying to suppress the melting point of component 2, right? My solvent, right? And so you can't think about it as my component 1 mole fraction increases, right? My system's melting at a higher and higher temperature. Okay, but let's flip this and look at ethanol, and hopefully it'll make more sense. Okay, so freezing point depression, right? I just flip things around, right? And I can solve for temperature. Okay. Cool. And so, the idea is, we add salt to our roads in winter, right? Salt being the component with the higher melting point. So it is going to be what'll, precipitate out a solution. Okay. But by adding acetaminophen to water, by having a mixture of, or not acetaminophen, we're not putting Tylenol on our roads, by putting salt on our roads and creating a mixture of water and sodium chloride, we decrease the temperature at which that system melts at. Okay. The other scenario we could look at is mixtures of say ethanol and water, right? So if I were to take a bottle of alcohol, right, your favorite beverage, right? It is possible if your beverage is strong enough to put it in the freezer and it doesn't freeze, right? Why? Because in mixing water and ethanol, we actually decrease its melting point. Right? Cool, right? So you can explain that with a simple equation, right? And so, what I'm going to look at is they have another sheet for water ethanol, right? And when we ran that, we got 2 plots, okay? So now we said that the component with the higher pure component melting point is the one that's going to precipitate out of solution, okay? So now in the case of water ethanol, water has a melting point of 0 degrees C. Ethanol is about negative 114. Right? So if I have a mixture of water and ethanol, water is actually going to precipitate out of solution first. Okay. So if this is water ethanol, and say I have a solution that is, I don't know, let's just say equimolar, 0.5 mole fractions water. Right? Well, actually, so if you start with pure water, right? Pure water freezes at 0 degrees C. if I have a mixture that's 0.5 mole fractions water and ethanol. Okay, so at 0 degrees C now it's a liquid, right? It doesn't freeze until I decrease the temperature down past looks like negative 50 degrees C, right? So as soon as I hit my saturation curve, then my system begins to freeze, where here that would be water would precipitate out of solution as pure crystalline water. Okay? If I were to take that system and quench it down to, say, negative 150 degrees C, right, what would happen is I would have a liquid with this mole fraction of water in equilibrium with pure crystalline water. Right? And so here it's water and ethanol, but you can think of something similar with salt and water in your road. Okay. So all I've done in this plot is, now this is water, ethanol. Again, water, component 1, which is what we're going to precipitate out of solution. But I'm expressing this in volume fractions of ethanol, right? And if you were to pick up a bottle of alcohol, the proof is essentially just twice the volume fraction. Okay. So if I had something that was 80 proof, that would correspond to 40 volume fractions of ethanol. Okay. And what that would tell us is, while pure water over here melts at 0 degrees C, right, this mixture is going to melt at a temperature less than 40 degrees C. Right? Call it, say, negative 20. Right? Something similar to that. Right? Cool. Okay. And the example we talked about in class is say ice beer. All right. So what happens in ice beer? If you have some sort of drink which is low proof, right? So it's going to freeze at some temperature close to 0. But if you were to bring that temperature down to, say, negative 50 degrees C, right? What's going to happen is water, pure crystalline water, is going to precipitate out of solution, and your system's going to re-equilibrate, in which you have a liquid, of ethanol and water in equilibrium with pure crystalline water, right? And so the idea would be then that now I have this liquid which is 0.8 volume fractions, say, of ethanol, and I could just filter out the crystalline water, and I'm left with a much stronger beverage. Same kind of concept of ice wine, where grapes are left down the vines late in the season, and you get water crystallizing out of that juice, which you filter out. You can also concentrate, I suppose, orange juice and things of that nature in this way. Okay, but that's a general idea in terms of reading and interpreting these sorts of phase diagrams. Cool. And with that, take a look at the notes. I'll post the notes on Canvas 2, right? But even walks through an example of freezing point depression. So I had a student once that was a big fan of Jameson, right? So drink, again, that's 80 proof. And so we'd predict freezing point of negative 18 degrees C. Experimentally, it's apparently negative 27, right? But you can go through the exercises on that.